Hello, this is Michael Sulak again, and in this video we're going to be looking through Chapter 4. Chapter 4 is a bit of a leap because now we're going to be looking at the relationship between two variables. And looking at two variables simultaneously opens up a whole nother world of what you can do in terms of analysis, in terms of making predictions, in terms of making decisions. So section 4.1 is called Scatter Diagrams and Correlations. You might also see the word plot. So all of this analysis is going to be talking about using quantitative variables. And if you think about, say, maybe the relationship between the weight of a car and the miles per gallon of that car, that's something that car manufacturers are definitely interested in. They want cars that get good gas mileage, and the lighter they can make their cars, the better the gas mileage they get. So they might be interested in studying two quantitative variables like miles per gallon and weight at the same time. So just to give you a quick rundown of what a scatter plot looks like: a horizontal axis and a vertical axis. And you would have your two variables. Say we were using the weight of a car as one variable and the miles per gallon of that car as the other variable. And when we draw a scatter plot, we use 1 point for each car. Maybe there was a car that had a weight of 3,000 pounds. Maybe that car has a miles per gallon of 25. So you would just see a point at the intersection of those two, and that represents that one car. And just as a reminder, when you are writing the coordinates of a point, the coordinates being a value for the x-axis and the y-axis, that the way you write this is you write the x value first and the y value second. So I would represent this car with 3,000, 25. And that's a car that has a weight of 3,000 and a miles per gallon of 25. And so generally in a scatter plot, you wouldn't just see a single point. That's pretty boring. So you would include a bunch. And if you think about how the weight of a car affects the miles per gallon, if we had, say, 10 cars in our data set, what that might look like is something like this. As the weight of a car increases, generally that car gets lower miles per gallon. So we could say as the weight goes up, the miles per gallon of our car goes down. But again, this is statistics, and statistics is a science. We are going to want to think of this relationship between these two variables, weight and miles per gallon. We're going to want to quantify this idea of as one increases, the other decreases. We're also going to do a process called linear regression, which we'll talk about more later. But the general idea is that we're going to what we call fit a line to our data. By fit, I just mean come up with a line that we could use to make predictions, to predict. Maybe we want to know, suppose a car weighed this much, and we didn't actually have any data for a car of that weight. Well, this line is going to give us a way to come up with what we think, what we expect, what we predict the miles per gallon of a car would be for a car of this weight, whatever that is. Maybe it's 2,500 pounds. So ultimately, our goal here is to come up with a tool, this line, which we're going to call, potentially strangely, a regression line, which is just a line used to make a prediction of one quantitative variable, in this case the miles per gallon, using the value of another quantitative variable, in this case the weight. So like a lot of things in statistics, there's a small amount of vocabulary we need to know. We talked about that we're going to be looking at two variables. We're going to call one the response variable, and we're going to call the other one the explanatory variable. So let's think about, we had weight of a car and miles per gallon of a car. Well, which one explains the other? It's a little bit more natural to think about the weight of a car explaining the miles per gallon of a car, because it's responsible for how efficient that car is. If the weight goes up, then that is sort of causing the miles per gallon to go down. So in this situation, it's fairly natural to think about the weight as being the explanatory variable and to think about the miles per gallon as being the response variable. And when we draw these on scatter plots, we draw the explanatory variable on the x-axis, and we draw the response variable on the y-axis. So here's another example from the book. So we have two variables. What are they? One is the depth at which drilling begins, which they're going to call x here. And it's interesting to notice that there's a unit here. Those are feet. We have a bunch of values of a depth in feet in this data set. And then we have another variable, which is the time to drill 5 feet, which they're calling y, and that's in minutes. So we have what? We have a data set of size 12 of these two quantitative variables. The first thing we'd like to do is just to get a better story of what is the relationship between these two. So we would make a scatter plot. So let's look at what that looks like. So here we have that data, and it's not the world's most exciting scatter plot, but notice that we have the depth down here, which if this was a better drawing, it would be labeled with the unit. Always good to put units on there. And then we have the time here, which is in minutes. The first thing to notice is that there is a bit of a pattern here. This isn't just dots kind of randomly all over the place. We could say something describing the relationship between these two variables. Generally, as the depth you're drilling goes up, the time it takes to drill 5 feet goes up along with it. So right now we're just sort of looking at this story and thinking about how this variable, depth, seems to be affecting this variable, the time it takes to drill 5 feet. So here's a picture of some of the more common relationships between the explanatory and the response variable. The first thing to notice is that 2 of these are what we call linear relationships, and 2 of them are what we call non-linear relationships. This is a linear relationship, and you could specifically say it is a positive linear relationship, which means that as x goes up, y goes up as well. And then this linear relationship here is a negative one, which means as x goes up, y goes down. So we saw a negative linear relationship when we were looking at weight of a car and the miles per gallon of that car. So let's just try to think for a second of 2 variables that might have a positive linear relationship. Here's one. The time you spend studying and your, say, percent grade, maybe in this class. I think generally if you could quantify these, as people spend more time studying, your grade typically goes up. And then notice these 2 down here, they are relationships, but they are non-linear relationships. So you can have 2 variables be related, but not in a linear way. And 2 variables I like to think about that have this sort of a shape, if you do that, if you look at them, would be, say you're driving your car and you're looking at the speed that you're driving, and you're looking at the miles per gallon. If you're driving low speeds, your miles per gallon isn't that great. And eventually at a certain speed, your miles per gallon sort of gets a maximum, the most efficient speed for your car. And then when you drive faster, your miles per gallon gets lowered. So these 2 variables, they are related, but they're not linearly related. And we're really looking, when we're going to think about making that line, that model, that prediction model that I talked about earlier, we're going to be wanting variables that are linearly related. So you have two non-linear relationships here, and then this last one is really just saying, hey, if you look at two variables and they're just all over the place, then that's not linear, that's not linear, that's just no relationship. Like if you looked at the relationship between shoe size and IQ, you are not going to see any discernible pattern there. There's no correlation between how big someone's feet are and their IQ. So just like if we're trying to think about where the middle of a variable is, we want to quantify that maybe with the average or the median. If we want to think about the relationship between two quantitative variables, we're going to want a number to represent that. Here's the book's definition, and a lot of this we can just ignore. This other name for it is not a big deal. The fact that the population is represented by the Greek letter rho is not actually something we're going to use in this class. So the important thing is that there's something called the correlation coefficient. This is just a number, just like the mean is a number. And what does it do? It measures the strength and the direction of specifically a linear relationship between two quantitative variables. And the letter that we use to represent the correlation coefficient is, for whatever reason, it's R. So this is just like the mean and the median. This is another statistic. So the correlation coefficient is a measure of the strength and direction. And what do we mean by that? You could have two variables that positively related, and we would call that the direction. Maybe they have sort of a loose positive relationship where the overall pattern is a bit more broad. Or you could think maybe those two variables are in a more tight cluster. And so this one you would call maybe a weak relationship, and this one is a stronger positive relationship. And similarly, you could have two variables that have negative linear relationships, and the weak negative linear relationship would be more spread out. Again, the direction is really just whether it's positive, as one variable goes up, the other goes up, or negative, as one variable goes up, the other goes down. And then the strength is talking about whether they're in a more loose cluster. These are both weaker relationships, or whether they're in tighter clusters. And these ones are these stronger relationships. So the linear correlation coefficient, which we said is called R, has a formula. And generally, if we find this thing, we're going to be using our calculators to do it. But I just want to look at this formula very quickly, just so it sort of looks like some stuff we've already seen before. And I don't want you, when you calculate this in the calculator, to feel like it's just magic. What is it doing? It's adding up a bunch of stuff. And we've talked about how S is the sample standard deviation. And now we have two variables, so we have two sample standard deviations. We've talked about X bar being the sample mean. Well, now we have two variables, so we have two sample means. We've talked about how n is the sample size, and the x sub I and the y sub I are just the data values. So we're just doing this for every single data point. Just like the standard deviation requires us to do a calculation for every data point, so does the linear correlation coefficient. It's just a number, R is just a number, and it comes from looking at two variables and doing some calculations with them. Let's look at some characteristics of this number, which we're calling the linear correlation coefficient, or sometimes just the correlation coefficient. So the first one is that this number, at the very least, is going to be -1, and at the very most will be 1, and it has to always be in that range. That's just a a property of that formula we just looked at. When you do that formula for any data set, no matter what, you will always get a number between -1 and 1. These second two, I'm not super worried about. We're sort of throwing a lot of information at you, so I'm just going to forget about them for right now. But these are the important ones, is that the closer R is to 1, the stronger the positive association is. And the closer it is to -1, the stronger the negative association. So sometimes I just like to draw a lovely little picture here where I'm like, okay, let's just look at what R can be. It has to be between -1 and 1. And at the very middle is 0. And if R equals 0, that means there's no linear relationship. So you remember, it might be something like you could have this sort of relationship, or you could have maybe no relationship at all. Both of these shapes, whether it's a curve or whether it's just a random cloud, are not a linear relationship. So we might be expecting R to be close to 0. It might not be perfectly 0. And then the closer you get to 1, the stronger in the positive direction. And the closer you get to -1, the stronger the relationship in the negative direction. So that's just a quick picture to think about this thing known as the correlation coefficient. So let's just look at some pictures of what we might see in a data set and what the corresponding value of the correlation coefficient would be. So here are some data points that are just happen to be perfectly in a straight line. And if you see that, it's rare. It's possible though. And if you ever saw two variables that were related like this, these are all scatterplots, by the way. If you saw two variables related like this, the correlation coefficient would be exactly equal to 1, the highest it could possibly be. And then if those variables, a little more realistically, weren't perfectly in a line, but still positive, you might see a correlation coefficient close to 1, but not perfectly 1. Here's a perfect negative linear relationship, which results in a correlation coefficient of exactly equal to -1 if it's actually perfect. And then if you had two variables that were still negatively related but not perfectly, then that R just gets a little bit closer to 0, maybe around 0.9. And then again, like I said, if you just had a cloud of data points, that's no relationship at all, which would give you an R close to 0. And if you had data that were related but not linearly, you would also get an R close to 0. So this is kind of important. If you get an R close to 0, it doesn't necessarily mean you're in this sort of situation where your variables aren't related at all. It just means you don't have a linear relationship. So you could be in this sort of a situation where your variables are related, but they're not related linearly. So the last thing I want to say is that R measures the correlation, which is just the association between two variables. And that is not the same thing as one variable causing the other to change. For example, here's a graph. On our x-axis, we have the number of pirates in the world. On the y-axis, we have the average temperature of the world. And look at these two variables. Are they correlated? Yes. Then as the number of pirates changes, the global average temperature is changing. And furthermore, that relationship is somewhat linear. If you looked at this data set, you might get an R. Notice that this x-axis is terrible. They've actually gone from the biggest number to the smallest number. But none of that really matters. What matters here is that there is a correlation. R is not going to be 0 for this. It's not going to be close to 0. The R will indicate that, hey, there is some association between the number of pirates in the world and the average temperature of the world. Is that a causal relationship? Of course not. Pirates are not causing the temperature to change. That is absurd. So people make this mistake all the time. They see two things that are associated and they want to make this jump and say, oh, well, one is causing the other. And you can't do that. That is really, really dangerous. All we're measuring with the correlation coefficient is, are they associated? Are they related? we're not talking about a causal relationship. Okay, I hope that was helpful, and until next time, this is Michael Sulak signing off.